All right, so the topic for today, I think it says on the schedule something like background on Lie groups and actions. This is basically, this course strongly encouraged you to have some background in Lie theory, and those of you who do might find this lecture quite boring. But it's not something I wanted to take totally for granted, that you knew about Lie groups and Lie algebras. And they're pretty important for the next section of the course. So I just wanted to make sure we had kind of gotten everything straight with that, talked about possible landmines in that area. So, a very common theme throughout all of mathematics, but one that's especially important in symplectic geometry, is symmetry, right? So we've talked a bit about symplectomorphisms and this sort of stuff, but it really is a very important theme. And since we're in this world of smooth manifolds, the right kind of symmetry to look for is, well, symmetry is usually expressed as an action of a group, and a group in the world of smooth manifolds is what's called a Lie group. So by definition, a Lie group is a smooth manifold, which is also equipped with a group structure such that, so here, the convenient way to write this is not with either the multiplication or the inverse map, but the map of A and B goes to A times B inverse. So this lets you say in one map that both multiplication and inverse are smooth. You can work out from this that inverse must be smooth, and so you can compose this guy with inverse to get the multiplication. This is just one of these things that makes us feel more clever. We can sort of, group in some category. Usually you want one where inverse multiplication is a morphism in that category. All right. I guess there is an important exception to this. I don't know if we'll really have any time to talk about this, but there are what are called Poisson Lie groups. So we're going to talk after break about Poisson structures, which are, sort of generalizations of symplectic structures where you have a Poisson bracket on your functions. It doesn't necessarily come from a symplectic form. And actually in that category, the right notion of group has an inverse versus the Poisson bracket. Sometimes some categories have a kind of notion of anti-morphisms. I think when I was in graduate school, some of us decided these should be called heteromorphisms. So that is something you have to watch out for. If you're in a category where the right thing for inverse to do is reverse structure, then you don't want just A times B inverse to be a structure preserving that. But for smooth manifolds, that's not a concern. All right, So what are the classic examples of these? And again, I sort of apologize to everybody who has taken a Lie groups course, but it's sort of worth going through these examples. So kind of the example to always have in mind is GLNR. So that's an open subset of matrices. It's the matrices whose determinant is not 0. And so by definition, it's a manifold, right? Any open subset of Rn is by definition a manifold. And this multiplication map, A times B inverse, well, there's a formula for the entries of B inverse in terms of the entries of B, which are rational functions. This is the cofactor expansion. And there's a formula for the product entries, and everything is a rational function in the entries of A and B. It's a rational function where the denominator doesn't vanish because it only involves dividing by determinant. So it's a well-defined rational function, so it's smooth. An important theorem about Lie groups, which is very, very useful for finding examples, is if you have a Lie group and you have a subgroup. So note, I'm not saying anything about manifold structure. A subgroup, which is closed, just closed in the usual sense of point set topology, then that will again be a Lie group. So, you know, somehow if you have already know one Lie group, and we found one very easily, kind of all of the obvious subgroups of it are probably going to be closed under the usual topology. All of those are automatically Lie groups. So for example, inside GL2R, there's the matrices which I think of R2 as C, and I think about multiplication by unit complex numbers. So in sort of more matrixy terms, I would ask my matrix to be 2 by 2 orthogonal with determinant 1. Well, those are closed conditions, right? Being an orthogonal matrix, that's a polynomial condition on the entries of your matrix. So that's a polynomial on the entries of your matrix being 0, that's a closed condition. And similarly, the determinant being 1, that's a closed condition. So these guys are going to define a closed subgroup, and so it's automatically a Lie group. Of course, you can pretty easily check by hand that this is a submanifold as well. But it just kind of makes your life easier. You don't have to check. It's automatic. And I certainly won't go into the proof, but it's sort of a very important idea about things with symmetries, right? That, you know, the proof is, the way to think about it is basically, well, if I have something inside if I intersect some number of level sets of smooth functions, then I get something which is generically smooth. At a generic point, the sort of subspace cut out by those differentials has the same rank at all nearby points, and my 0 level will be smooth. So, you know, generically near a point, some number of them will be redundant, and the level set will be a smooth manifold by the implicit function theorem. Now, there can be lots of bad points. Suddenly, what's this? New linear dependencies between the differentials of the functions show up, and those can be sort of bad points, singular points that don't have a manifold structure. But if you're a group, then you can use group multiplication to go between any pair of points. So if you have a group, any 2 points have to have the same local structure because you can multiply by a group element to get from one to the other. So if any point looks locally like a manifold, they all have to look that way. So that's kind of the intuition behind this. This is a really useful observation that, you know, if you have something that has a transitive group action on it, in particular, which has a group structure, then sort of all points have to look the same. And so you can't have a bad point. All right, so what are other things we can do? Well, we can look at GLNC. Now, you can also think about that as an open subset of a manifold, C to the n squared, you know, with the condition that the determinant is not 0. And you just have to remember that you're thinking of everything as a real manifold, but you can also think of GLNC as a subgroup of GL2NR via this thinking about complex structures that we've done before. So you take R2n, it has a standard complex structure that makes it into Cn, and you want to look at linear maps of R2n to itself that commute with that complex structure. So they're complex linear. So you can write that as just it commutes with this matrix J. All right. You can also look at the orthogonal matrices. or which is, matrices whose inverse is equal to their transpose, right? That's a closed condition. You can look at the unitary matrices, which are the intersection of that with GLNC. So this was something that was covered on your homework, that the unitary group is this intersection. And there's also this symplectic group, which is all the matrices that preserve the standard symplectic form on R2n. And let me note, both the orthogonal and the unitaries have a subgroup that maybe people consider a bit more often, the SO and SU, which is where you require the determinant to be 1. One reason that SO is often considered is that this is connected. It's a connected topological space. ON is not, has 2 components, which are, of course, the matrices with determinant 1 and determinant -1, or orientation preserving and orientation reversing. Similarly, actually, GLN-R is not connected because it has one component where the determinant is positive and one component where the determinant is negative. On the other hand, GLN-C is connected. All right, so I was going to make a little point about this symplectic group. Now that I've written this, I kind of worry that some version of this was on the homework and I don't really remember, but let me just sort of say it out, right? I need to assure you that this symplectic group is a closed subgroup of GLN, or GL2n, I should say. And probably to some of you, that's just obvious. Somehow anything that involves equalities like that, that's a closed condition. One way to think about it is you can write out this equation for every pair of vectors VW. Every one of those is a polynomial condition on the entries of A, and so it defines a closed thing. There's also sort of a useful way of thinking about this where you say, oh, wait a second, I can write out the standard symplectic form in terms of dot product, right? So we had this equation, using sort of the kind of notation we had before, I would have written something like, this is G of V minus UW, but I'm on R2N. So my inner product is just dot product. And so I'm taking this expression and writing it in terms of dot product. And I can do the same thing for AV and AW. And so I have actually a pretty nice kind of manifestly polynomial expression for what it means to be a symplectic form. And this is just this condition I wrote up above applied to all pairs of vectors in a basis, right? The entries of these two matrices are just the symplectic form applied to, and the symplectic form after multiplication by A applied to all pairs of vectors in a basis. All right, are there any questions about these examples? As I say, this is probably deathly boring for some of you, but this is one of these things that I think it's good to be reminded of from time to time, even if you knew it before. Another thing is just slightly random, but maybe worth knowing about. It's not true that every Lie group is a subgroup of GLN-R. You can actually prove that there are Lie groups that have no injective map into GLN-R for any n. But almost all Lie groups that you would ever think about do. So I just gave you a bunch of examples that live in GLN-R, and sometimes even ones that don't obviously live in GLN-R can be embedded in there. So another kind of obvious example of a Lie group is think about Rn itself as a manifold with the group structure given by addition. Now, again, you can very explicitly check that everything appearing there is smooth, right? Inverse is just multiplication by -1. Addition is just coordinate-wise addition. So that's obviously a Lie group. But it also has a at least not totally obvious embedding into GLN plus 1R, which you can sort of think of geometrically as, okay, Rn acts by addition on Rn in kind of the obvious way. I embed Rn into Rn plus 1 as the level set 1 for the last coordinate, where xn plus 1 is equal to 1. And then I can extend that action linearly. So this is sort of a useful trick for going between linear and affine actions. So this is a general trick for taking an affine action and turning it into a linear one, where you add one more coordinate. For your affine action, you always set that last coordinate to be 1, and then you can extend it to a linear map on the bigger space. The general formula for this is if you have an affine transformation that looks like V maps to AV plus X. So here V and X are vectors. Then you can turn this into the matrix. Here's A, here's 0, here's X, here's 1. So that's an embedding of the affine group into the general linear group. We're here. The affine group on Rn is all transformations of this form. All right, so that's one more interesting example of a loop. Here, I put my tea in a travel mug this time, but now it's too hot to actually drink. Okay, as I said, we're mostly, at least my kind of motivation for thinking about Lie groups is mainly that they appear as symmetries of things. And the basic mathematical notion that we use for that is that of a group action. So if I have a group action on a manifold, that means I have a map from G times M to M, and I want that action map to be smooth. The Canis de Silva, and I should emphasize here, when I say action, I always mean left action. And this is one of these kind of annoying things that shows up over and over again, that there's a notion of left action, notion of right action. You kind of just have to choose which one you prefer. And then there are lots of annoying constructions where you're like, oh, this is more naturally a right action, so I have to mess with it a little bit to get a left action. I'll note here, Canis de Silva says that this is a homomorphism from G into diff M, from G to diffeomorphisms from M to itself, which is gotten here in this action map by holding G constant and looking at the induced map from M to itself. But then she still has to write things down in terms of this action map to say what it actually means to be smooth. So this diffeomorphism group you should think of as some kind of infinite dimensional manifold. And I would like to say, oh, this is a smooth map from G into diffeomorphisms, but then you have to answer some tough questions about what does it mean for a map into diffeomorphisms to be smooth? So it's kind of more convenient to just say, hey, this map is smooth, the action map. One of the most important examples is that if I have a Lie group, it acts on itself by left translation. So this action map sends the pair GH to G times H. Or I have an action by right translation, but I want a left action, so it has to be right translation by G inverse. So the right translation from G inverse by G inverse, it means I take H and I multiply it by G inverse. And exactly the issue here, right, is that I want that G1 times G2 times M to be equal to G1, G2 times M. And the fact that I multiplied them in this order, G1 times G2, that's what makes it a left action, right? It's they sort of multiply in the right way if I write the thing that's acting on the left and the thing that gets acted on the right. And if I reversed my conventions about that, well, then it would be natural to reverse what order I multiply G1 and G2. So indeed, if I take R1, G1 inverse composed with R G2 inverse applied to some H, right? I do right translation by G2 inverse first, then I do right translation by G1 inverse, and that's equal to H times G1, G2 inverse. And you just have to do these sorts of calculations a few times to like get straight in your head how left and right actions work. And so there will be various other places where I have to throw in an inverse. And it's always because it's something that was kind of actually a bit more naturally a right action. And I have to throw in that inverse to fix it and make it a left action. All right, the other really important example of this is the action of GLN R on Rn is smooth. So the same is true of any subgroup of GLN acting on any submanifold of Rn. Right, and again, this comes down to the formula for how a matrix acts on a vector is a polynomial of the entries in the matrix and the entries in the vector. So it's a smooth map. Now, we've actually already talked a lot about one particular example of an action, which is a flow. So an action of R on a manifold, that's assigning a diffeomorphism to every element of R that satisfies this homomorphism condition. And well, we've talked a lot about such flows. They've been very useful for us and will continue to be useful for us. And so somehow like the point of the lecture today and some of this upcoming stuff is, well, how do we take stuff that we did with flows and somehow upgrade that to more complicated Lie groups than R? So in particular, we've done a lot of thinking about flows by thinking about, oh, actually, for every complete vector field, there's a flow gotten by exponentiating that vector field, by calculating the integral curves for the corresponding ODE. How do I sort of generalize that notion to actions of more complicated Lie groups? Well, obviously I'm going to need some more complicated notion than just a vector field, some way to generalize vector fields. And the thing that does that for me with Lie groups is the notion of Lie algebras. So you'll see a few different ways of thinking about what the Lie algebra of a Lie group is. I kind of like to start with, as a vector space, it's the tangent space to the group at the identity. So it's a vector space, its dimension is the same as the dimension of the group as a manifold. For example, for GLN, this is all n by n matrices, right? GLN is a submanifold of n by n matrices thought of as a manifold. And so its tangent space at that point can be identified with the vector space itself. All right, but there's another really important notion, perspective on the Lie algebra, which is I can also think of it as the space of left invariant vector fields on G. So left invariant vector field means that for any group element, when I push forward by left translation, I get back the same vector field for all G. So note, this means in particular that if I fix its value at one point, I can get its value at all other points by pushing forward by left translation from the point where I started to the other. So in particular, if I fix an element of the Lie algebra, a tangent vector at the identity, I can construct a unique left vector field by taking the derivative of left translation, going from the identity to the tangent space at G, and pushing forward my vector by that. So here, TLG is the map from the tangent space at the origin of G to the tangent space at G of G from taking the derivative of the left translation. Okay. And again, you'll note here, I again had to make an annoying breaking of symmetry. There's also a right invariant vector field corresponding to each element of the Lie algebra. And so some people will define the Lie algebra as the left invariant vector field. Some people will define it as the right invariant vector fields. Some people will define it as the tangent space at the origin. And all of those things are in canonical bijection with each other. But this thinking about it as left invariant vector fields gets us something very nice, because there's an operation we know on vector fields. We can take the Lie bracket, which again, I'll just remind you, that means sort of I look at the difference between evolving with respect to the first one and then the second versus the second one and then the first. So I'll have some vector field. Maybe I'll draw X this way and Y this way, right? And the Lie bracket is exactly the difference between going along X and then Y, going along Y and then X. So this is Y, this is X. And then the sort of failure of this guy to close up, that's the Lie bracket XY. We can also write that as the Lie derivative with respect to X of Y. So it's about the failure of the flow with respect to X and the flow with respect to Y to commute. All right, so taking the Lie bracket of two left invariant vector fields, gets me another left invariant vector field, because taking Lie bracket commutes with push forward, right? Doing the flow commutes with push forward, so the failure of the flows to commute also commutes with push forward. So this gets us an operation on the Lie algebra of bracket.
I have a question.
Yes, of course.
I've seen this proof that the Lie bracket is the same as the Lie derivative, but do you have any intuition for this? I mean,
well, you know, somehow it's just taking this picture and thinking about it differently, right? So it's saying, you know, what's the Lie derivative of y with respect to x? It's how does the vector field x, y change when I push it forward by the flow of x?
yeah.
Right. So that stays constant if and only if the flows commute. If flowing with y after I flowed with x is the same as if I flowed with y first.
Yeah. Thanks.
So it's just kind of, do you think about this guy where I failed to close up? Do you think about it here at the end? Whoops. Or do I sort of do inverse push forward by the flow of y and think about it over here? And of course, it's, you know, I'm taking a derivative of the failure to commute as the time gets smaller and smaller and smaller. So, you know, somehow you shouldn't read much into the fact that these guys are drawn in different ways.
Okay. Thanks.
Right. What's the? And I think this is one of these things where if you really write it out sort of carefully, then it's kind of tautological. But right, the Lie bracket is about what happens if I I'm not doing this very well. You know, if I flow for x with time 1, flow for y with time 2, I'm also worried that I'm going to slip in a sign somewhere, but let me at least write some version of this. Even if there's a sign mistake in it somewhere. Right, so Lie bracket is sort of about the failure of this composition of flows to close up. So like this is approximately flow by the Lie bracket. Oh, I made a mistake here. I shouldn't have done different times. You know, this is approximately flow by time t by the Lie bracket, right? And you know, these kind of different formulations of it are just kind of manipulating this guy. So, like, you can also think about this as, what does it mean to flow with respect to y? And then this guy is the flow with respect to the inverse push forward, so pull back, but I'm not supposed to pull back vector fields, the inverse of push forward of y, right? So comparing these two terms is exactly what Lie derivative with respect to x does.
Yeah.
Okay. That's probably the best explanation I'm going to give off the cuff here.
Yeah. Thanks. Yeah, because I saw the proof and it's like it was a very long proof that I didn't get much intuition from, but this is very helpful. Thanks.
And the other way to think about this, right, is vector fields you can really think of as operations on functions, right? So, somehow I have a vector field, but I also have the operation of Lie derivative on functions, right? And one way to define Lie bracket is to say that if I look at the commutator of these two Lie derivatives, then that itself is the Lie derivative with respect to a vector field. So you can define a vector field as basically an operation on functions that looks like a directional derivative, satisfies the Leibniz rule. And you can check that this left-hand side satisfies the Leibniz rule, so it gives you a vector field. And we name that vector field the Lie bracket of x and y. And then like this fact that the bracket is the same as the Lie derivative of y with respect to x is like the Jacobi identity, essentially. So this is kind of another useful way of thinking about all of these things. All right. So what I was going to write out is that this gives me a bilinear map from the Lie algebra times itself to the Lie algebra, which satisfies these properties that we wanted. I'm just reminding you of the definition of a Lie algebra. One, it's bilinear. It's skew symmetric. And it satisfies the Jacobi identity. And when you think about it in terms of left invariant vector fields, it just inherits these properties from the fact that Lie bracket of vector fields has those properties. And I'll just note here for GLN, the Lie bracket of x and y thought of as matrices is just literally commutator as matrices. Some amount of work is required to figure out why this is so. The way I like to think about this is essentially that. So if you, yeah, what is the right way to think about this? Yeah, okay, let me not actually try to explain this because what I was going to say doesn't actually make sense. I'll explain this better in a little while. All right, so one thing that's going to be very important for us is that when I have a G action on a manifold, every element of the Lie algebra gives me a vector field on the manifold. So if the element of the Lie algebra is called X and the manifold is called M, I'll call it X sub M. And what I do is when I want to know what this vector field is at a point P, well, I look at the action map. So there's a map from G to M, which is act on the point P. That's a smooth map of G into M. So it has a derivative, and I hit my element of the Lie algebra, thought of as a point in the tangent space, with it. So that gives me a vector field xm for every element of the Lie algebra of my group. And very annoyingly, you might expect that this would be compatible on the nose with Lie bracket, but you would be wrong. This drives me slightly crazy, but the way that all the conventions are set up, if I take the Lie bracket of X and Y as elements of the Lie algebra of the group, and then I turn them into vector fields, and I take their Lie bracket on the manifold, I don't get the original Lie bracket turned into a vector field on the manifold. I get its negative. And this is this crazy thing about right versus left invariant vector fields. So the kind of important thing to know here is if I look at G acting on itself by left translation, then I can look at what this vector field is. I still have this vector field, which if I look at my definition, means that at H, I look at the map LG from G to G. Wait, I'm now worried that this is not working out right. I was really sure I had done this correctly. I hate being that guy who's like, oh no, wait, this is wrong. But I think I did get this. So in order to define this vector field, right, I'm looking at the left multiplication action for LG of this guy. So I should be looking at TLG. From tangent space. And I send X to X sub G. So I'm concerned here because this looks exactly like the definition I had of left invariant vector fields. My guess is that that definition was wrong, but since we don't have an enormous amount of material to cover today, let me sort this out, but it's after 45 past. So let's take a break now. I'll ponder this issue for a moment, and I think we'll straighten things out. What I believe I should get here is that I should get that this is a right invariant vector field. And right invariant vector fields have the opposite Lie algebra structure from left invariant vector fields. So it's very easy to get sort of the Lie algebra structure backwards. But I will double check about that rather than trying to figure it out live here. So let me just pause for a moment.